Okay, so I want to take a look at a couple of projectile motion problems here, and I want to discuss optimal angle for maximum horizontal distance. Um, so when we're looking at this, we've talked about horizontal or projectile motion problems a little bit, and they're relatively straightforward problems. Usually it's just the same equation every time. And what I'm going to always tell you is whenever you're doing one of these problems is to draw a picture of what's happening. Okay, that's my first step always, so I can sort of visualize. So I have a projectile that is launched at 30 degrees above the horizon at a velocity of 75 meters per second. And we want to know how far away does the projectile land with no air resistance. So we'll start by drawing a picture. So I've got some sort of projectile. I'll try to get it up here so I have a little room. And it's being launched in the air at about 30 degrees. Comes up, and then makes this nice parabola and lands at some unknown distance. We'll call that our x direction, right? And so we have some information here. I know that I want to get a velocity, and I have to get some sort of velocity going in the horizontal direction. But what I'm really going to do is usually I'll leave horizontal velocity until last. Usually with projectile motion, you're looking to try to solve for time, first of all. So let's kind of go through and figure out what we have here that we can use in the kinematics equation. First of all, I got 75 meters per second. That could be helpful. It's not in the horizontal direction or the vertical direction, so we have to do something with that. We have the angle of theta of 30 degrees. So that's going to be helpful in trying to solve for vertical and horizontal velocity. But again, I can't fit either of those into the kinematics equations just yet. So let's write down what we have. One thing I know for sure, since I'm going to be looking for time probably, is that when my projectile reaches the apex up here, the very top, it's going to have a zero final velocity. It's going to go from whatever it is here all the way up to here where it has zero velocity. So let's do that. Let's say our final velocity of the projectile on the way up is equal to 0. And then we also know that since there's something in the air, that we have an acceleration of negative 9.81 meters per second squared. We have initial velocity. Because I have horizontal here, or I have my hypotenuse here, and I'm looking for opposite. Anytime I've got something where it's going vertical velocity, in this case, I can use this as opposite over hypotenuse, or take the sine of theta. So I can take the sine of theta, in this case the sine of 30 degrees, and since this is my hypotenuse and it's opposite over hypotenuse, I can take sine of 30 times 75, sine of 30 degrees, and we'll multiply that by 75 meters per second. And again, that's for the vertical velocity, my initial. And then the last thing I have is that I want to get time, because in order to solve for distance, I'm going to have to multiply my horizontal velocity times time. So t equals what I want. Okay, and we're missing s for distance. And so for a kinematics equation, we would use final velocity is equal to initial velocity plus your acceleration times time. And then we'll manipulate that to isolate time. So v minus u, let's get that u over there, and then we'll divide that out by the acceleration. That should equal my time. So let's solve that first. I'm going to take 0, and then I'm going to subtract out the sine of 30 degrees times 75 meters per second. And then I'm going to divide that whole thing by my negative 9.81 seconds. Well, not 92, I guess meters per second, so negative 2 meters squared. Okay, and let's figure out what we get here. I have 30 degrees. Sine of that times 75, so that's 37.5 meters per second, and that's negative and then I'll divide that by 9.81. Negative, I get this equals 3.82 seconds. Now, one thing to remember is that's the time it takes to reach the very top here of the parabola. But since there's no air resistance, you'd have an equal time going down. So I'm going to multiply that times 2, and that should give me my total time in the air. So that comes out to about 7.65 seconds. Okay, so that's my first thing. So now I need to find, in order to get horizontal distance, I just need to take my initial horizontal velocity times time. Now what I want in this case is I have hypotenuse, but what I want is my adjacent. So this becomes cosine, right? Adjacent over hypotenuse. So I can get my final answer by saying cosine of 30 times hypotenuse, adjacent over hypotenuse, and that's 75 meters. And then we will and that's going to equal, oh, I'm sorry, we're going to multiply that by the time. So 7.65 seconds. Okay, so here we go. 30 cosine times 75, 64.95 meters per second, and then we'll multiply that by 7.65 seconds. Is going to be equal to 496.9 meters. So we'd probably say about 5.00 times 10 to the second meters would be our answer. Okay. All right. Now, the point of this video is that not to show one more projectile motion question, but I also want to know, what's the optimal angle if I want to get maximum horizontal distance. So we did 30 degrees. So now let's do the same equation, and we'll use 45 degrees and 60 degrees, and we'll explain why 45 degrees is going to give us the maximum distance. And so let's start with 45 degrees. That'd be easy enough. I'm going to do the exact same equation I had here. Launch. This one will be a 45, and then this one, launch, and this equation is 60. Okay, so for this first one, we know that both of them are 75 meters per second to the -1. So in this case, my initial velocity is 0, my acceleration equals 9.81, we want time, and my initial velocity is going to be the sine of 45 times 75. Okay, let's see what we get there. 45, the degree angle gives us 0.707 times 75. So this is equal to 53.0. And then we want time, and so we're going to use our equation, this kinematics equation, where right here, V equals U plus AT, and then we'll manipulate it, V minus U over A equals T. So my V is going to be 0 minus 53, and then we'll divide that by 9.81 negative, and we get 53 divided by 9.81, 5.4 seconds times 2 gives us 10.8 seconds. So first thing that's kind of interesting is that I have quite a bit more time in the air than I did at 30 degrees. I have 10.85 seconds. And then I'm going to take the cosine of 45, and we'll multiply that by 75, right? So we're going to get the velocity, and then we're going to multiply that by 10.8 seconds. And that should give us the distance, total horizontal distance for 45 degrees. So 45 cosine is 0.707 times 75 times 10.8. So this gives us 572.8 seconds. Okay. So now one thing I noticed about that is that the cosine of 45 degrees, 45 cosine times 75. That gives us a horizontal speed of 53.03 meters per second. The cosine of 30 times 75 gives us a speed of 64.95 meters per second. So 45 degrees gives us a slower horizontal speed, but it also gives us a lot more time. And so that extra time mounted to about 75 meters. So the extra time was very useful there, so that you kind of have a balance there. Now let's do this last one. Again, I have a velocity, or a final velocity of 0. I have acceleration equals a negative 9.81. And I have my u would be the sine of 60 times 75. And then, which is going to equal 60 sine times 75, gives me 64.95 meters per second. Okay, so that's my initial vertical velocity. So that's a lot higher than the other one. So 30, I had a much lower initial vertical velocity. So now, when I go to do time, since time is equal to v minus u divided by acceleration, or 0 minus 64.95 divided by 9.81. 64.95 divided by 9.81 gives me a time of 6.62 seconds, and then we'll multiply that by 2, and that gives me a time of 13.24 seconds. Now that's a lot more time in the air, right? This one gave me a time of 7.65 seconds, so it reached about 500 meters. This one gave me a time of 10.8. We reached about 572 meters. This last one, I have a lot more time in the air. So let's see what our cosine is to find out what horizontal speed is. So I have cosine of 60 times 75. That gives me my horizontal velocity, and then we'll multiply that by 13.24. We'll see what we get. 60 cosine times 75 times 13.24 gives me 496.5 meters, which is exactly what I had over here. Okay, so the trade-off, even though I had a lot more time, the trade-off was that my horizontal speed was a lot less. In this case, my horizontal speed was a lot higher, but the time was a lot less. So the reason that 45-degree angle is perfect is because the sine of 45 degrees equals the cosine of 45 degrees. That means that whatever your horizontal, or whatever your hypotenuse speed is here, it's going to be equal for both the vertical velocity and the horizontal velocity. So whenever you're trying to get maximum distance, now this is of course if you don't have air resistance, so sometimes air resistance plays a role in this, but with no air resistance, maximum distance horizontally is always set when you can get the angle at 45 degrees, because that gives you an equal velocity vertical and an equal velocity horizontal.